Today we're going to be talking primarily about workflow issues and actually just going over some basics on how we transfer back and forth and looking at ways to avoid errors going back and forth between this. Now, the programs we're going to be using today are Revit Structure 2012 and the RISA-Revit Link for 2012, which has recently been made available on our website as a free download. We're also going to be taking a look at RISA Floor 5.1 and RISA 3D 9.1, which are the programs we have that interface with Revit 2012. Now, the topics we're going to be covering today are the following. Number one is workflow. We're going to talk about what different ways you can move back and forth between the two programs and how you can sort of maximize your efficiency by doing this. We're going to take a look in the Revit model at what considerations do you need to make in your Revit model, specifically with things like the analytical model, such that when you transfer to RISA, you're going to get the best transfer possible. We'll take a look at mapping files, which control how things are mapped back and forth between the programs. And lastly, we're going to take a look at what you can do in RISA in order to get your RISA model to most properly import into Revit. So the big question always comes in, should I be starting in Revit or in RISA? And the answer to that is either. You can really go from either program into the other and back to the original one, which we call round tripping, with no difficulty, or at least very little difficulty depending on your experience level with the link. One thing I'd like to point out right out of the gate is that there is a learning curve associated with Revit and with interfacing Revit with any sort of analytical software. So certainly the last thing that I would hope any of you would do is have a major project coming up where you say, okay, I'm just going to learn how to interface RISA-Revit on the fly because I have this thing due Friday and I'll just figure it out by then. It typically doesn't work like that. We get a lot of technical support calls with a lot of the same questions. There is a learning curve associated with it, and you should definitely sit down and play around with the link a little bit before you actually dive right into it and rely on it in a critical situation. It is a very robust link, but we find a lot of the same mistakes get made by users again and again. And we're going to talk about some of those mistakes today. But there's one thing that is important is nothing is a substitute for actually practicing with this link. So I definitely recommend trying it out. So the question as to whether to start in Revit or RISA, well, we're going to first take a look at what happens when we start in Revit, and then we're going to take a look afterwards at what you need to do in order to start in RISA and bring your model over to Revit. The other big question that always comes in is, what elements do I transfer? A lot of folks will instinctually think, okay, I just want to transfer everything from this model to the other model. But there's a lot of extraneous data that is in some cases useless from Revit going into RISA, and in some cases can actually hinder you when you're working in RISA or transferring from RISA back to Revit. So it is important to be very selective about what you transfer back and forth between the programs if you want to get the best usage out of the link. So let's go ahead and open up Revit 2012 here, and what you can see is I have a model that I've created. This is a sample model which we can use to discuss how we're going to transfer back and forth. Now, before we even go over to RISA, let's just take a look at this model and see what we're working with here. What we have is a multi-story building with moment frames running in one direction and brace frames running in the other direction. Now, if I go down here to, say, the second floor, what we're going to see is I have concrete beams laid out for most of this building, and then I have some steel framing around this circular atrium area. Now, on top of that, I also have some walls as well. These are going to be concrete shear walls set up. And on the upper floors, say the fourth floor, here we're looking at all steel, and this is intended to be composite steel. And then lastly, once we get up to the roof, we have this dome situation set up with a truss using these hanger rods as the tension members in the truss. So I have tubes of these roof member rafters and these hanger rods coming down. This is the sort of design you see typically in airports and things like that. We're going to discuss how we can take complex geometry like this and get it into RISA with no problem. Now, bear in mind that we could also have laid this whole building out in RISA to start with and then imported it into Revit with no problem. So you can really start and end either way. So let's take a look at one thing here. In the Revit model, I'm going to come up to Manage here and open up this Manage Links. And what you're going to see is that I've linked a model into my Revit structure model. This is called the architect's model. The architect's model contains everything architectural about the building. So there's a lot of elements that come from Revit structure, anything from doors and windows to lighting and carpeting, all sorts of things that as a structural engineer we do not care about. But the architect has supplied us from his model with a couple of important things, and that is the grids for the building, that is where the column lines are, and he's also given us the elevations of each floor level. And so if I come and take a look here, say at the overall building elevation, what I'm going to find is here's these elevations, and these have actually been linked from the architect's model. Now we have a foundation listed here at 98 feet, but that 98 feet that we see here, that elevation is actually what's called a project elevation. I can confirm that in the elevation view by clicking on it and clicking on this edit type here. What you're going to see is that we are 98 feet above the base for my project, but the project is local to my machine. If I want to take a look at what the architect's using, I'm going to take a look at his shared coordinates. And that is the coordinates that have an origin based off the architect's model. Typically, if you're coordinating with an architect, they're going to give you a set of shared coordinates for the model. And what we'll find is that the architect is calling this elevation 725 feet, something he probably got from the surveyor. And you can actually tell this by sort of scrolling out here. You'll see I have this point way down here. We're looking at an elevation out in sort of 2D space. This is called my survey point. This is what the architect defines as elevation 00. Whereas up here, we have my project base point. This is locally what I'm calling 00. So you can work within either different coordinate system and transfer back and forth with RISA. It's just important that you decide which coordinate system you're going to stick with and actually stick with it. Now in this case, you'll note that when I was working with my project coordinate system, that we had an elevation here at the foundation of 98 feet. And that's basically nominally 2 feet below the 100-foot base elevation that typically architects and engineers are going to use for their initial floor level. That allows us to prevent having negative floor elevations, which are not only confusing on drawings, but also can cause problems with RISA, since RISA floor does not support negative floor elevations. So whenever you're setting up a building in Revit, it's important to always go with positive values. And that's why I usually will start with the ground floor at elevation 100. So this is sort of the first part of this. The next thing to take a look at is the orientation of the building. Now if I come back in here to say the second floor, and we're taking a look at this view, what we're seeing is basically in north direction straight up and down here. So the building is facing straight north. But that's actually what's known as project north. This is just for the convenience of drawings. If we flip through here, we can actually orient the building towards true north, and we can see that true north is up in this direction. So a Revit project can have both a project north and a true north, which are separate from each other. Now, when it comes to exporting to RISA, I'm probably going to want the building to be set up orthogonally like this. The reason behind that is that RISA is going to generate wind and seismic loads in the global X and Z directions. And that's going to be running this way and this way. And it makes much more sense for the analysis of my brace frames and moment frames to have wind going parallel to them rather than having wind come in at these sort of oblique angles, which will make it difficult to check everything. So we're going to work with Project North in the case of this Revit model. Let's take a look at some other aspects of this. If we zoom in, you'll see that I've modeled all these beams here in Revit Structure, and I've modeled them all as W8 by 10s. The reason I've done that is because W8 by 10 is a beam size that, in practice, I would never use, typically because the beam is so shallow that you can't easily fit a 2-bolt connection on it. But what I did was create all these beams in here as W8 by 10s so that when I go over to RISA and come back, if one of the beam sizes does not come back from RISA, this will immediately jump out at me on my plans before I actually submit them for bidding, say, as, hey, this beam was not updated. Now, RISA Revit Link does have a warning mechanism incorporated that warns you, hey, this beam size did not come back for whatever reason, but if you happen to miss that warning when you're going through, this is sort of my double safety net that I have set up. Now similarly, I have the columns all set to be a W14 by 808. Once again, a size that in practice I would never use on here. So that's just a little trick that I've picked up from working within the link here. Something new in Revit 2012 is the ability to view the analytical model much more clearly. What I've done is pulled up a 3D view of this analytical model. Now, for those of you who are not familiar, in Revit you have two items really. You have a physical beam and you have an analytical beam, and the same goes for columns and walls and braces and everything else. So when we come out here and take a look at the physical model, what we're looking at is these elements that have all sorts of complexity to them, and this is where we can control things like how far they are offset from the roof level, a variety of different physical attributes, what the actual cut length is for a beam, things like that. But when we take a look at the analytical model, we're taking a look at what RISA really cares about. We don't care about all the specific end detailing of how a beam is coped or the such. As far as RISA is concerned, this beam is just a stick. And so what we see right here is the stick model that's actually going to be imported into the RISA program. Now that Revit 2012 has this automatic 3D analytical model view, you can actually come in here to troubleshoot your model before you export it to RISA. Let's take, for example, the braces that we have here. If I take a look at this north brace frame elevation, what we see is that I've laid out some brace frames in this building. When I click on this, you'll see that I've set the work point for the physical brace to be at the intersection of the center line of the column and the center line of the beam, so that when it comes to detailing out my gusset plate, I'm going to have no eccentricity whatsoever. It should be very easy to design that. However, what we can do is turn on the analytical model. For that, I'm going to open up the graphic overrides in Revit. You can just hit VV to activate this very quickly. And I'm going to go to Analytical Model and turn on the Analytical Model. And when I hit OK, what we're going to see here, if I flip to a wireframe view, is a colored line representing where all the different analytical pieces are. I'm going to shut off the display of floors here for a second so that we can see more clearly what's happening. So I have this beam right here. This beam is offset from the finished floor elevation by 6 inches, as we can see. However, this orange line, this is the actual analytical beam. So physical beam down here, analytical beam up here. The reason for that is we want all the analytical, or all the beams to line up on that floor level for the actual RISA analysis. When it comes to the analysis in RISA, the fact that this beam may be offset 6 inches and this one may be offset 5 really has no major effect on things. However, you'll note that when we drew this brace in here, well, the analytical line for the brace did correctly match up at the top there. Down at the bottom, the analytical line is coming to where the beam actually intersects. Now, this is technically the most accurate representation of where the brace is going to go. However, if we model this in RISA, we're going to have this eccentricity here, which is going to produce quite a bit of moment and shear in the column and probably cause it to fail, when in reality that's not going to be there. So what we can do in Revit is we can come over to the analytical model here, and there's this excellent new tool whereby I can click on the analytical line for the brace, and I can hit this button up here, Analytical Adjust. And what this does is give me little node points for the end of every analytical member. So I can click and drag the end of the brace up to this point right here, the beam column intersection, and there, now we've corrected the analytical model. And when I hit Finish here, now everything's fixed, and when I go back over to my brace frame dialog, what we see is analytically, this is what RISA is going to see. In terms of the actual construction, it's disconnected right here. But that's fine. That's actually not an issue, because even though our analytical idealization for RISA is not exactly matching up with the true geometry, we're only off by a degree or two here. So we can expect that things are going to be close enough that this simplification is going to really be worth our while. Now, the next thing you may note is that when I took a look at the overall 3D view of the structure, we had this canopy floating out here in the front part of the building. This canopy is completely disconnected from the building, but we've modeled it in here because, as typical, for one structural job, we're going to have one set of structural drawings, so we want to show everything structural in it. At the same time, though, I do not want to analyze this canopy in conjunction with the building. Rather, I'd like to do a completely separate structural analysis for it. So what I've actually done in this case is I've disabled the analytical model on this canopy. So with any element that we have, like say this beam right here, when I click on it, you'll see now in Revit 2012 we have this checkbox, Enable Analytical, and it's unchecked. That means that even though these beams and columns are here physically as structural elements, I don't want to analyze them. So when we come over to the analytical model, there's nothing there at all. This is a very handy way of turning on and off different things that are labeled as structural, but we don't want to come over to RISA. Another great example would be, say, if I had some brick fascia on this building and I had all sorts of brick frames on here, single angles and channels and things like that I don't want to take into account for my overall building design. These are more components and cladding. I could shut off the analytical model and keep those from coming over and keep them from getting in the way of the rest of my model. Let's take a look at a couple other common things here. If we take a look at the columns in this structure, if I click on a column here, you'll see that every column has a base level and a top level. Similarly, every wall, when I click on it, has a base constraint and a top constraint. It's important that you set these and that you set them correctly in the model. So for example, this column starts off at the second floor at a base offset of 0, 0, which is to say at the bottom of the column is at finished floor elevation. And the top of the column is at the third floor, but it's offset downward 6 inches, and that's to account for the slab depth here. So that is correctly defined. But what I see happen all the time is folks will come in and say that this column's base level is the second floor and that its top level is, say, the second floor with the top offset of 12 feet. You'll see we're going to get a warning right here initially saying that it's going to unjoin that column. The problem with defining this is that graphically it would look correct if that column is starts off at 0 feet above the second floor and ends at 12 feet above the second floor. But in RISA, we're not going to consider that column as going from floor to floor anymore. We're going to say, okay, this column is effectively 0 height because it starts and ends at the second floor. So it's very important that you define things like this where we have the correct top and base level. The same thing with the wall here. You can choose for top constraint unconnected, and I see a lot of folks do this. And when you set that, what that means is that we're not going to consider that because it's a cantilever wall that doesn't go from floor to floor, and RISA set up more so to design these as sort of bearing and shear walls in your structure, not necessarily cantilever retaining type walls. The next thing we'll take a look at is the elevation offset of beams. And so for that, I'm going to go up to my 4th floor here, and we're going to take a look at a section cut that I've put through the building. And if I zoom in here, what you're going to see is I've got this joist and this metal deck set up at elevation low roof. So low roof is defining the top of deck or the finished floor elevation everywhere. This is how the architect has set this up. And we can see I have an 1.5 inch metal roof deck. So I need to offset my joists downwards by 1.5 inches. In order to do that, I have two options. Number one, I can use the start and end level offsets that we have listed here. Otherwise, I can use the Z direction offset. Now, start and end level offsets I see people frequently use, but these are really set up intended for sloping roofs. So if this joist started off here and ended 4 feet higher on its other end, then I would say the start level offset would be 0 and the end level would be 4 feet, and that would allow me to slope my roof here, which RISA will support. However, if I just have a uniform offset downwards due to geometry reasons, say the depth of this deck here, instead what I want to use is what's called a Z direction offset. And that means I can offset this downwards 1.5 inches, and that's going to account for the depth of the roof deck on there. And the nice thing about the Z direction offset is that RISA doesn't care about it. So even though we have this offset down 1.5 inches, when we come into the RISA model, it will show up at offset 0. Basically, everything will be at the floor level, which greatly simplifies the analysis. And so it's definitely something that we want to do. Now, similarly, this girder that the joist is riding on, I have that offset down 4 inches, 1.5 inches for the roof deck, 2.5 for the joist seat. But I use this Z direction offset so that I can keep things graphically looking correct here for when I want to cut my details for my actual drawings. But analytically, when we take a look at that same portion of the building, we see everything intersects here at one nice common node. so we don't have to mess around with the vertical offsets of the actual beams. Now, another thing to take a look at when I'm in this 3D view, I have these decks defined. I've set up this 1.5" metal roof deck, and you'll see that I actually have this deck curved where it comes around inside of the atrium. However, when I come to my analytical model, and we take a look at that same location, you'll see it's more octagonal. We have these straight lines defined everywhere right along here. Well, this is important because when we go over to RISA, we cannot have curved slab edges. RISA needs to have straight slab edges in RISA floor. And so I had to basically fake the program out. The way I did this was I defined one deck in the 3D model, which is curved. This is going to be used for my drawings. And if we take a look at it, I've unchecked the Enable Analytical on here. What that means is that RISA is going to entirely ignore this deck. But if I turn on the hidden elements, what I've really done is I've defined a second deck, which I've hidden from my physical view, but which we see in the analytical view. And this deck right here is an analytical deck. It's just hidden from this physical view, so it doesn't show up in any of my drawings, but it does show up in the analytical model. And this is the deck that we're actually transferring back and forth with RISA. The next thing we're going to talk about is wall openings. This is another important and often overlooked thing within the program here. We can transfer wall geometry and wall openings back and forth to RISA. If I scroll down here and we take a look at this wall here, right now it's just a flat wall with no openings on it. We can, however, add openings to it, but it's very important how we do this. A lot of folks will immediately go to the edit profile for the wall, and they'll actually define a donut-shaped wall by having a profile on the outside and a profile on the inside. But that is not the way to handle it. Instead, what we need to use is what's called a wall opening element. So I'm going to flip over to my south elevation of the building here. And in order to add a wall opening element, I need to come up here to my Home tab, and what we see, if I just double-click on this one right here, is that I have accidentally set the tab the wrong way. Here we go. We're back to it. So now I have this wall opening button right here, and what this does is it cuts a rectangular opening in a straight or curved wall. Now, we don't support curved walls, but we can do a straight one. So now I'm going to click on the wall, and then I'm going to click and define my opening on this wall. And so we can see right now that it's actually cutting a hole in this wall, but it's doing so by creating this element that we have. Let's go back to the 3D view to see this a little more clearly. So here's the wall, and here is the wall opening. And I can hit Tab and select only the wall opening, for example. So this is how we have to define openings when they're going to go back and forth to RISA. So we'll leave this in here, and we'll see how that works out. And then the final thing we're going to take a look at before we transfer over are the materials. So when I click on this column, for example, and I scroll down, we're going to see that this column is defined using a Revit material called Metal Steel ASTM A992. And if I open up the material browser that's within Revit here, we can see that there's a wide variety of different metal materials that are in here. These all map over to RISA, however, they do have certain limitations. So, for example, what Revit calls ASTM A992, when we come over to the Structure tab here, you can see Revit sets certain properties, such as the minimum yield strength or minimum tensile strength. But it's missing certain other properties that RISA is going to care about, especially when it comes to things like seismic detailing. So when we go over to RISA, we're going to see where the shortcomings come in with these Revit materials and how we can overcome that. So I'm going to go ahead and close out of that material browser now. And let's take a look at one last item here. I have these tension rods defined here up on this dome. And you'll note that what I've done is I've created them as beams, but I've given them a structural usage of horizontal bracing. So there's different structural usages available in Revit. You can call things a girder, joist, other, or purlin. And for these four options, girder, joist, other, and purlin, we treat them all as beams. But for something labeled as horizontal bracing, we're going to call that what RISA knows as an H-brace. The important thing about H-braces is that they do not get imported into RISA floor, since RISA floor is not doing any sort of lateral design. Instead, they get imported into RISA 3D. So when we import to a RISA floor models always have a 3D model embedded underneath them. This means that this piece is going to get imported directly to the 3D model embedded underneath RISA floor, much as these braces will. And we'll see that when we transfer over here. The other important thing to consider is the mapping file that we have. So let me go ahead and open up here a mapping file that we have available. So I'm going to come on to my C drive, and in there is the RISA folder and the RISA-Revit Link 2012 folder. And in here we have this document, RISA-Revit Mapping File.xml. I'm going to go ahead and open that up. And what you'll see here is this is an Excel sheet that we have that you can update yourself that maps RISA shape names to Revit shape names. This allows us to transfer back and forth between RISA and Revit and get the correct shapes lined up between them. Because as you can see in RISA, we would call this tube an HSS 10 by 5 by 6. They would call it an HSS 10 by 5 by 3/8. It's very important to consider all the little syntax of the way that these symbols and letters are done. Even capitalization is important. So when we scroll down here to the bottom of this list, what we're going to find is I've created in my mapping file my own custom mapping. This Revit shape name called 1-inch rod, or 1 quotation rod as it were, is something that I've created custom within Revit, but I can actually map that to bar 1.0, which is the RISA internal code name for a round 1-inch bar. So when we transfer over, that is going to correctly transfer. So let's go ahead and run that transfer right now. I'm going to come up to Add-ins up at the top, and once you've installed the RISA-Revit 2012 link in Revit, you'll have these buttons available under Add-ins. And I'm going to choose Export to RISA. This is going to bring up this dialog box where we have a variety of options. I can choose whether I want to go to RISA Floor or RISA 3D. I'm going to launch the program directly. I don't want to export selected items only because I want to export the entire model. I'm going to export it using the shared coordinate system as opposed to the project coordinate system. We looked at that earlier. And I'm going to orient it to project north, not true north. Then we're going to come down here. I'm going to choose to redesign the members. That is to say, I don't want to analyze this existing building with these W8 by 10s. Rather, I want RISA to come up with more optimal designs for me. I do want to export the walls out to this model. I do not have any footings or boundary conditions in this model, so I'm going to leave this unchecked. I don't have any loads defined in this model, so I'm going to leave those unchecked. But I do want to bring over the slabs and openings. So that'll work. And then I need to choose where I want to export this to. So we go down to Exchange File Name, and I click Browse. And I'm going to go ahead and throw this in a folder right on my desktop here as my temp folder here for this presentation. So this is where we can define this location. Now, one thing you can always do is set this as a network location so that if you're working with Revit on one machine and RISA on another machine within the same office, you can share back and forth over the network by just setting this up as a network drive or a network location as opposed to this local drive. We'll go ahead and export this out to RISA Floor since RISA Floor has some more advanced capabilities that work with Revit. But we can similarly do things with 3D, and we'll take a look at that a little later. So I'll hit OK, and now we're going to get a progress bar that pops up that tells us exactly what's happening. And because I have RISA and Revit installed on the same machine, it's actually going to launch RISA Floor for me directly. So now RISA Floor is going to pop up, and we're going to have our model pre-populated. And if there were any errors or warnings, they would have popped up. But of course, because I'm an experienced RISA-Revit Link user, to say the least, there weren't any errors or warnings. However, I can guarantee that if it's your first time using the link, you will have gotten some sort of error or warning on that first transfer. And incidentally, we do have another webinar that's already been recorded that's up on our website that goes over troubleshooting those specific errors and warnings that you can take a look at another time. So for now, we're in the RISA Floor model, and I can come up and take a look at my full model view. Now you'll note that the grids are way down here and the building's floating up above them. That's because the grids in RISA Floor always appear at elevation 0, but if we take a look under the floor spreadsheet, our second floor elevation is at 743. That's because we used that architect's elevation. but that's fine. We can zoom in here, and we can see that the model has imported. Now, if we take a look at the dome, we're going to see that all those tension rods are not present, and that's because we define them as H-brace, horizontal brace members. So therefore, they're only going to exist on the RISA 3D side. Similarly, our vertical braces are not present in this building either, but that is once again because we've defined them as vertical braces, so RISA floor doesn't need to care about them. So let's just come back into a plan view here. And the first thing that we're going to take a look at in this model and RISA floor are the material properties. So I'm going to come over to the data entry toolbar, and we're going to open up the material spreadsheet. Now, those of you who are familiar with using RISA know that there's about 5 materials that come standard in RISA as the default materials we create, and these are these 5 right here. But we've actually imported all of the materials from the Revit model as well in this case, and we can see them all listed here. So now we've got this giant mess of materials, and we'll see that the RISA default for the shear modulus is this value, whereas the Revit default is that value. Different values of Poisson's ratio. We can see that there's actually a problem with one of the Revit materials. Revit has incorrectly defined the density of it and the thermal expansion coefficient. So we've got a bit of a mess on our hands here. What I usually like to do is clean up the materials spreadsheet when I transfer back and forth. You can also clean this up by actually going back to Revit and changing the default materials that are in your template file so that when you create new Revit models, it doesn't create them with all these goofy materials. But in this case, we'll just clean this up. It's fairly quick and easy to do. So first off, with the shear modulus, if I leave this blank, the program will automatically calculate it. I'm going to highlight this entire column, and I'm going to right-click and say Fill Block. This is a tool in RISA that we can use to fill all of the selected cells with whatever value I enter in here. So if I leave this blank, it will fill all these cells with blank. That's good. That means the shear modulus will automatically be calculated. Next, we're going to fill all the Poisson's ratios with 0.3, which is the correct value. We're going to fill all the thermal expansion coefficients with 0.65, and we're going to fill all of the densities with 490 pounds a cubic foot, 0.49 there. Now, I've only used a couple of different steel materials in my Revit model. I've used this Revit A36, which I assigned to all of my tension rods. I can confirm that by coming back in here and hovering over the beam material listed, metal, steel, ASTM A36. I've used the A500, round and rectangular, and I've used the A992. And I haven't used anything else. So the first thing I'm going to do is I'm going to get rid of all the other Revit materials that are extraneous. This is going to allow us to purge them out of both models. So I can just highlight these right in the spreadsheet, and I can say Delete Marked Lines. I'm not using any grade C here, and I'm not using any of these other miscellaneous metals. So now I've purged these out. Now, not only have I purged them out on the RISA side, but when we go back to Revit, it will also purge all those unused materials out of my Revit model and sort of clean things up. Another thing, though, is we have these values for RY, RT, and FU. These are all used for seismic detailing, and Revit doesn't know a thing about those. However, they are correctly set as defaults for my RISA materials. So what I'm going to do is I'm going to highlight all of these and copy, just right-click copy in here, and I'm going to paste them into the A36 that came from Revit. So I can come in here and I can say paste, and now it correctly populates those values. Except for the fact that I pasted over density, I was in the wrong cell. Let's undo, come back, and paste that in there correctly. So I can actually come through and correctly paste all these materials in and get the correct yield strengths and FYs and FUs and such. In this case, we'll skip over that step since I've shown you the basic idea behind it, and I'm going to delete the remainder of the RISA default materials. So we're left with only the Revit materials that we were actually using. Similarly, under the concrete tab, Revit's got about 100 different concretes that it defines, but if I delete all of the concretes out of here, except for this concrete 4,000 normal weight, any concrete that I brought in from Revit will automatically default to this material. So now we've got all of the materials correctly set up and got it all working right. The next thing we want to take a look at is decks. Now, when we come over to the RISA model, I had actually hidden some decks that I assigned to this upper roof so that we could see things more clearly, but you can see these deck panels that I've placed on there. These all get imported into the RISA floor model. And I can take a look at that by coming up here to the Show Decks button on the toolbar. And we'll see as I hover over each deck, it's going to tell us down in the little status bar here what I have. So 1.5" metal roof deck all around there. And as I come down to the different floor levels that we've created, we can see here's my metal roof deck. On the 4th floor, we have this blue composite deck that I've got set up. So a variety of different decks. However, if I go to the deck definition spreadsheet, we'll find that Revit doesn't quite know all of the analytical properties of decks that RISA is going to care about. So we have to fill some of these in ourselves. So for one thing, there's 3 decks that we're going to be using in this. The 6-inch concrete, 3-inch lightweight composite on composite decking, and 1.5" metal roof deck here. And so I should really come in and correctly set all of these values. So for the concrete here, I'm going to copy just these properties right here from my flat slab default deck and paste those in so we get the correct analysis. And for the composite deck, I'm going to copy the properties from that composite deck down onto the Revit one, but I could fill these in if these were different. And these values right here are irrelevant for the metal roof deck. It won't care about them. Next, the concrete is actually a 2-way span on that 2nd floor, so I want to tell it that it can actually go 40 clear feet with no problem. The composite deck will give it a max span of 9 feet, and the roof deck here will give it 6 feet. And the program will warn us if it's spanning any farther than that. And by putting 1 here, what I'm telling it is that any beam underneath this deck is braced every foot on center. The other thing I need to do is set up loads. Revit really doesn't care about the loads for these decks, but we do here. So for one thing, I want to say that my 6-inch concrete flat slab, it has 2-way load attribution. The other 2 are going to use 1-way attribution. And I need to tell it the self-weight. This is a very important step that a lot of folks miss when they transfer back and forth, but just bear in mind that Revit has no idea about the self-weight of a deck. Similarly, we're going to give it a construction live load so that we can check that, and I'm just going to do that by highlighting these cells. Once again, right-click, fill block, and when I put in 0.02, that gives us our 20 PSF construction live load listed on there. Okay, what's next in the model? Well, if I come into my columns spreadsheet here, I'm going to see that rather than bringing in column sizes, the W14 by 808s, what we've done is we've given it a design list. So I've told the program, rather than giving me W14 by 808 columns, I want you to design to wide flange columns. That's what that redesign members checkbox did. However, if I tell the program to design using wide flange, that means that it's going to pick out of the entire database of AISC wide flanges. And that's not exactly valuable to me. I want to have column shapes, and specifically, in terms of detailing, I want all nominally the same size column shapes. So what I can do in this spreadsheet, actually, is highlight this entire chunk here of wide flanges. And I'm going to right-click and fill block once again, and I'm going to type WF space 12. And this is just an internal program code, but you can find this just by clicking on any one of these and learning what the design lists are. What this is going to do is design all my columns now as nominal 12-inch wide flanges. So it's only going to use the 12-inch column shapes from the AISC. That'll turn out much better. Another important thing to consider is that when we came over into RISA, RISA Floor is capable of doing composite design, and so we assume that all beams in the model are going to be designed compositely. But if I come up to the cone roof here, that's going to be under roof deck, so I don't want these beams to be designed compositely. I'm going to highlight the composite column. Once again, fill block, leave this blank and hit OK, and blank unchecks all of that. So we want to shut off the composite behavior for the cone roof and the high roof in this case. Next, we're going to come in and do that for the low roof, but I'll show you an alternative way to do that here. If we come to the low roof, I'm going to come up to Modify Beams, and we can go to the Modify Design tab of Modify Beams, and I'm going to have Composite unchecked. I'm going to say use this right here and apply this to all selected beams, and that will uncheck Composite for all those beams that we had on screen there. Next, we're going to go down to the 2nd floor, and we're going to change all of these wall panels that I have to be concrete. So I'm going to come in here, say Modify Wall Panels, and we're going to say we want to use a concrete material, and I will apply that to all the walls. Furthermore, if I double-click on this wall right here, we see the opening transferred over from Revit. However, as a concrete wall, in the current version of RISA 3D 9.1, there's a limitation that we cannot design concrete walls with openings. Now, that limitation will be going away in the next version. However, for now, we're just going to delete this opening since it's so small that it's going to have a negligible effect on the overall shear wall design. So I'm going to delete that opening for our analysis. However, it's going to be important that when we go back to Revit later that we don't bring the walls back, because otherwise it will delete the opening in my Revit model. And we certainly don't want to lose that. We only want to lose it right here. Now, the other thing to consider is floor openings. You can see what looks like an opening here on the second floor, but in reality, we haven't defined an actual opening element. You can transfer openings back and forth from RISA to Revit, but you can only bring rectangular ones. So for odd shapes like this, I actually need to come in RISA, and I need to tell this that I have an opening right here. So I click within there, and that creates these openings for me. Another important thing, if I go to my diaphragms spreadsheet, the cone roof and low roof are both set up with rigid diaphragms, but we actually want those to be flexible diaphragms. So I'm going to flip that right in here so that we get a flexible diaphragm analysis for those upper portions. Next, I'll go to the floors spreadsheet, and I'm just walking through right here a lot of the common things that you need to go in and set whenever you come back and forth that you may end up missing. Splice type. This controls whether or not we're going to have fixed base columns or pin base columns. Currently, by default, they're all set to be moment, which is to say that they're going to be fixed base. But if I just type S for shear, now we're going to, let me come back here to fill block. I'll just type out shear. That's going to switch those all to be shear now. Also, we want to take a look at the loading that's on here. The default area loads, since we didn't bring it over any loads, are set up as office, but we actually want to set these to be roof for our roof levels. We can use office for the other levels. And these deck defaults, even though it says flat slab everywhere, we've explicitly defined decks which were brought in from Revit, so we don't need to worry about this. This is all entirely overridden. The deck default is only set up there to be the deck that's used if no other deck has been explicitly defined. Now lastly, we had set up those W8x10s. I want to make sure that I don't actually get any designs of W8x10s. So I'm going to come into my member design rules spreadsheet and tell it that I don't want any beam to be designed that's less than 9 inches deep. So that way it'll ensure we'll get at least W10s when we run our design here. Then I'll come to the load combination spreadsheet. We'll delete the existing load combinations because we're actually going to run an LRFD analysis on this using the US 2009 IBC strength with roof live load but no snow load. I'll hit generate, and then I'll hit solve on here. What's going to happen now is the program's running through each floor level, and it's iteratively designing and optimizing everything within here. Now, if we were in RISA 3D, we would get a straight-up analysis, and then we would have suggested shapes afterwards, and that's what we're going to see when we come into RISA 3D next. But for now, in RISA Floor, we're actually going to get a new analysis and an optimization for all of our member sizes right out of the gate. So this is running through floor by floor here, and you'll see we're at 4th floor. Next, it's going to go down to 3rd, and then 2nd, and we'll finally be finished with this. And it's going to take care of optimization for deflection. So if our beams are deflecting too much, it'll handle that. It'll design those joists for us. It's going to just get a wide variety of different designs that's going to transfer back and forth between RISA and Revit. So the camber is going to come in there. The studs are going to come in there. Basically, everything will transfer back and forth between the programs. So we're just about done with our solution here. It's just wrapping up. You can see the 4th iteration listed down there. And once it's done with these iterations, we're going to get a warning log that pops up. We get a few different warnings. First off, here's our cone roof. Deck exceeded maximum span. I'm getting this all over the place. Now, these warnings are important to pay attention to. If I come onto my cone roof, what we're going to see here is that this deck is spanning from roof beam to roof beam, and that distance that we have on there is about 12.5 feet. Well, that's a bit far for a 1.5-inch roof deck to be spanning with no intermediate support. So one option we would have would be to put in a bunch of purlins on this roof. But in this case, it's probably just cheaper to go with 3-inch roof deck and have it span between these beams anyhow. So I can do that by coming up to my deck definition spreadsheet, and I can actually add a 3-inch roof deck. And under the General tab here, I'll just tell it that it's going to be a 3-inch deck. And it can actually handle a 15-foot span with no problem. Now, another thing we want to do is if we take a look at the 2nd floor here, if I take a look at the decks that have been assigned on the second floor that came over from Revit, you'll see we have this 6-inch concrete here, and you can pull this data entry toolbar out of the way to see the color coding. 6-inch concrete flat slab on top of these concrete beams may not be quite adequate to span this 36 feet, so maybe we'll bump it up to an 8-inch slab. Rather than adding a new one, I can actually just make a change to that existing slab. I'm going to say it's now an 8-inch slab, and that it has a 100-pound per foot self-weight as opposed to the 75-pound a foot self-weight. Then we need to go back to the cone roof, and we actually need to assign that roof deck on there. So I'm going to come up here to Assign Decks, Modify, and we're going to say let's put this 3-inch roof deck on. And that's represented by the yellow, and I just click around here, and this puts our 3-inch roof deck up there to get rid of those warnings. Now, another warning that I was getting was related to deck span, and that was here on the low roof level. And what we find is that the deck is actually spanning too far right here. This is one of those handy deck span warnings. So what I should probably do is put in a tiny infill beam. I can draw this beam in, and then it's actually going to appear in Revit when we go back over there. So I'm going to come into Draw Beams, A992, Non-Composite Wide Flange, and I'm going to use my Draw Beam to Beam tools as opposed to the standard Draw Point to Point, so that I can actually tell it that I want to draw a beam that is horizontal starting at the end of this beam and going over to that beam. And it sticks this little infill guy in right here. So now we have that all set up. That should take care of a majority of the warnings. We'll run through one more solution, and this solution should go faster because now the program has some better starting sizes and better starting self-weights to go through, and we can see already that it's actually ripping through this quite a bit quicker. So now we're running through these solutions on here, and you'll note that I picked LRFD for the steel. That was what was chosen in my global parameters. We didn't go in there and look at it, but I can't pull it up while it's solving. I chose that because I also had concrete in this model, and so that made things easier. I can use one set of load combinations that works for both steel and concrete in that case. However, if I really wanted to use ASD for steel instead, I could have generated a second set of load combinations for the steel members, and that would have designed all of those using ASD as opposed to LRFD, but then we'd have to run through twice as many load combinations. That really slows things down. I don't mind running through it this way. Now our solution's just about done here on the second floor. What we're going to get is another warning log pop up once again. It's going to tell us some more important things. But one of the major things we're getting here, a lot of the same warning, beam has negative moment along its span, composite design not done. That's referring to our moment connection beams. So if we come in here to the moment frame beams that I've set up over here, these are all set up as fixed beams, and that means that they cannot be designed as composite beams because they have negative moment, and so therefore the composite action would be canceled out. How does the program know that these are fixed? If I come in here to show pins, you'll see we have pins on all these joists, but no pins shown at the end of those beams. That came from Revit. I was wise enough when I started this model to set up all of the moment frame beams as having fixed connections. So if I zoom in here and click on one of those beams, let's just get this one right here, we're going to see in its beam properties on the left here, this has actually been set up. It's not as a moment frame connection on here. And when we take a look at the analytical beam, we can set a start and end release of fixed and fixed, as opposed to beams in the other direction, which have an analytical of pinned and pinned. So once again, just sort of thinking ahead on that one in the model. I'm going to use my director tool and go into RISA 3D now. And here it's going to ask us for information about the wind loads and seismic loads. And so what we find is here is everything that is relevant to the RISA 3D model. Now, one important thing, here my whole dome is set up, and we can see all those H-brace members have now come in, so we can get a full finite element analysis on this one with correct stiffness. When I came in and set up this dome, in Revit, I called this centerpiece here a column. This is a structural column element. And so when we go over into RISA, RISA says, okay, that's a column, so it must have a foundation at its base. So it automatically places this boundary condition at the base of every column, which is great for us all around here. We don't have to go in and do that. But in this case, we don't want a boundary condition. We actually want this whole dome to sag due to its weight to get a correct design for that. So I'm going to come in and modify that boundary condition and tell it that it's a free boundary condition. And that effectively removes it and allows this dome to actually sag and give us the correct design in this case. Next thing we're going to do is take a look at the braces that we have here. Now remember, we came in and corrected this brace in the analytical model, and look at that, it lines up nicely. We did not correct the other braces in the analytical model, and so you can see they actually miss when they connect in here. And so this is all part of what I mentioned earlier, that what you see is what you get with regards to the analytical model and the RISA model. So here, this is actually coming in below that point, and in the RISA model, you see the exact same thing. This is why it's very important to review your analytical model before you transfer over to RISA to make sure that everything's lined up correctly. But let's just go ahead and roll with this. Now I'm going to come up here to Tools and run a full model merge. This is a nice tool that I wish was available in Revit, but unfortunately it's not. This allows the program to find places where beams almost connect to each other, but not quite, and actually trim or extend all of them to get the model to line up within a very small tolerance. And when I hit apply, you'll see that 93 different beams were trimmed or extended in order to get things to line up with a better tolerance than what Revit was giving us initially. The next thing I'm going to do is take a look at my materials. I can actually come up to my member color coding button up here and color code by materials set, and we'll see what I've got set up for all these different members in here. Now the labeling may be a bit much in this case, but we can see here what we've got, if I just set member labels to none, is all the different materials that have been assigned to our beams. So we're in good shape with this one here. I just wanted to confirm that the blue members here, these are my H braces, are all assigned to A36 and nothing else is. Well, those 1-inch rods are going to have a considerable amount of spag, so what I'm going to do is come into my materials spreadsheet and give those a density of 0 so that all of my H brace members, those little 1-inch rods, won't have any self-weight, and that'll prevent them from sagging and throwing off our solution. The other thing that's important to know is that currently in our model, the beams are all assumed to have 100% unbraced flanges and as such. The only information we got was some from RISA floor, but overall, when we come into the hot rolled tab of the member spreadsheet, you'll see that a lot of these beams in here have very long unbraced lengths. So we actually want to set those since Revit doesn't have that information stored in it. So I'm going to come up to my Draw Beams tool and go to the Modify Design tab of that. This is where we can graphically apply unbraced lengths to everything. So I can say, let's just go with everything being braced every 6 feet on center for the flanges and against oiler buckling. And then when I say Apply to All Selected, that will then apply to the beams within my model. Now the other important thing is I want to select just my horizontal bracing that's in there. And so for that, I'm going to come up here and find my bar 1.0 so that we can select only that bracing. And I want to tell it that that is oiler buckling. Oiler buckling is sort of like tension only, but it's better in that it allows those braces to take a small amount of compression. It's going to allow this model to converge much quicker. So now we've set that up. Let's take a look for a moment at the automatically generated loads that we have. If I turn on the display of load, you'll see first off, here's the dead load that came over from the RISA floor analysis. We can clearly see that two-way slab distribution down there and all those dead loads everywhere else. But we actually have a wind load that's generated as an uplift on that dome. This is an automatic load generation that you get when you link in with RISA floor here. So we can see this dome is actually going to get analyzed for an uplift area load that's occurring all over that sloped dome surface. So we just wanted to make sure that that was going to be considered on there. Next, I'm going to go into the load combination spreadsheet. We'll go to the load combination generator, and we're going to generate IBC 2006 strength gravity and wind combinations with the roof wind loads. And so here we have all of our relevant load combinations. Now, at this point, typically, I would run through an envelope or a batch solution and start analyzing and designing things in here. But in this case, just counting on where we are with time, I'm just going to run a single load combination so that we can get back over into Revit and talk about some other things. So I'm just going to solve this one combination so we can at least get some results. Ordinarily, though, we would start to work on the lateral portion of the model and go in and take a look at suggested shapes and optimizing them. But those of you who are familiar with RISA already know how to do that. Let's focus on the Revit instead. So now we finished our solution, and I'm just going to take a cursory glance and see. I actually see a couple columns that are failing, but not by much, so we're overall in good shape. Now what I want to do once I'm all set in RISA is I want to go back into Revit. So I'm going to come up here and I'm going to save my model. It's going to ask me a couple questions. It says RISA floor results are available. Would you like to save them? I have to say yes. If I'm going to go back into RISA, I have to have my results saved. So I'm going to say save the results, and that creates a separate solution file in the same folder as my model file. The same thing with the RISA 3D results. Yes, I must save my results. Next, I'm going to go up to File, Export, and in the current version of the program, it says Export BIM Exchange File. We're actually redoing this. I have a beta copy of the new update to the program where we just say Export Autodesk Revit Structure File. The behavior hasn't changed. We just did this to make it more clear that a BIM Exchange file is an Autodesk file. And so now I'm going to come back and I'm going to export this overwriting my previous Exchange file. It's important that once you start working with one Exchange file that you continually overwrite that existing Exchange file. You cannot go and start creating new ones. That's going to throw off the round tripping entirely. So it's going to tell me that already exists. Do I want to replace it? Yes. And even though it seems like it's actually overwriting it, what we're really doing is merging all of the information together behind the scenes. Now let's go back over into Revit. We need to be in a 3D view within this Revit model, and we're actually going to bring that information back in from the RISA side. So under Add-ins here, I'm going to go to Import from RISA. And I'm going to click the Help button here just so we can launch the Help document and read through a few things in it here while we're actually bringing this model back in. But what we'll see is that it automatically knows where my Exchange file is because it's in the same location as before. Now when we come back, I already said I don't want to update the walls because I deleted that opening. I do want to bring in end reactions, and furthermore, I want it to take any end reaction that's less than 10 kips and set it to 10 kips. That way we can show these reactions on plan, and I can be sure that the fabricator, when he designs all these connections, isn't designing any of them for less than 10. I didn't update anything with the grids, so I don't want to bring those. And I didn't update anything with the slabs and openings, so I don't want to bring those back either. Now this is one of the important things that I mentioned earlier when we were talking about what do we transfer back and forth, what elements to transfer. Well, ultimately, you want to transfer as few things as necessary. So if we didn't change anything with the project grids, let's not bring them back. We don't want to risk having any changes in our Revit model that may be unintentional. Furthermore, with the loads, yes, we could bring the loads in from the RISA model. However, they won't do us any good in the Revit model. There's nothing we're going to do with the loads over here. So why bother bringing them over? It's only going to slow things down and clutter things up. We want to have as smooth and clean of a transition as possible. And in fact, in this case, just for speed purposes, I'm going to say update member sizes only. This means that some of the geometry changes we made, such as me adding that extra little infill beam on the 4th floor, aren't going to come through. Ordinarily, I would have this unchecked and bring the full model back, but for the purposes of this presentation, I just want this to go quickly. So I'm going to hit OK, and it's going to start reading it. Now, there's other circumstances where I want to use that update member sizes only. In practice, once again, if I don't need to bring back geometry changes, if I haven't changed anything in the geometry of the building, there's no reason for me to do a full geometry import. All it does is just multiply the chances or the likelihood that something may go wrong. And those of you who have used the link before will know that just due to the inherent complexity of Revit and the way that everything interacts between RISA and Revit, things can and do occasionally go wrong. Now, we do get warnings about everything that goes wrong, so it's not that things are going to be hidden from you, but rather it's just a fact of the matter of working with any sort of link between two programs that are inherently different. Revit's set up to produce drawings, RISA's set up for analysis. It's apples and oranges, but we share as much information back and forth together as we can. Now, while this is coming through and updating all of our member sizes, let's just take a look at the help document here that I pulled up. And we actually have a printed version of this as well that's in the RISA-Revit Link folder. So if you ever want to print this out, it's right here under your C RISA-Revit Link 2012. It's called the RISA-Revit Link User's Manual. It's a PDF. We also have it available on our website, so you can have a printed version of this if you want to work through it. But in this help file, what we do is we go through first off and explain what the intention is behind the link and what the idea is and how you're supposed to use it. But furthermore, we have this great workflow topic that's been written up where we discuss in much more detail than we have time for in this webinar, really what are the advantages and disadvantages of starting in Revit or starting in RISA Floor or in 3D? How do we round trip back and forth? And we put together some great examples in here where you can take a look at how can I most efficiently use this link. Here's an example where we have this situation. What should I do in that particular situation? We talk about problems with workflow. How do we sort these out? This is a great troubleshooting resource that you have available when you're working back and forth within here. Now, beyond that, we also have a Getting Started topic in this help file, and that's going to get us through sort of the basics of how do we jump right into it. Obviously, if you don't remember all the steps that I'm taking right now, that can be useful to you. And we have some appendices, including the mapping file appendix. So we took a look earlier at how I mapped that 1-inch rod back and forth between RISA and Revit. I did that by coming through here and taking a look at the exact nomenclature that I'm supposed to use. So in this appendix here, we have this bar underscore shape. That's how we transfer a bar back and forth between. And this talks about all the details on how you should format your mapping file and set this up. Another common one that we'll run into is if we take a look in the RISA model, what we'll find is that we have these joists up on the roof here. And these were all designed to 16K3, 18K3, so on and so forth. But if I had dropped a point load on one of these joists, it would no longer be a standard 18K3, it would be a special 18K3 or an 18K3 SP that you would normally point out on your structural drawings. If we tried to bring that back into Revit, we're going to get an error that it cannot find a Revit joist called 18K3 SP. So your choices would be to either create that joist size on the Revit side, or you could come into your mapping file and tell it, hey, if you find an 18K3 SP as the RISA shape name, map that to a regular 18K3 on the Revit side. It's just important that you remember that you need to put on your drawings that that is a specially designed joist, since it's going to have a large point load dropped right on it. Here we can see we're still continuing with the layout, and so it's definitely a quicker transfer back and forth to get just the member sizes only, as opposed to bringing the full geometry back and forth between the programs. But even so, with a larger structure like this, we have a lot of data that we're passing back and forth. And of course, Revit is spending this whole time as well sort of checking all this data and validating it to make sure that everything makes sense, so it doesn't end up destroying your Revit model, because the last thing we want to do is have either model get ruined back and forth in the transfer. That's one of the things that definitely, especially in recent years, the newer Revit links have been able to take advantage of some additional tools that are behind the scenes in Revit that allow us to get a much smoother and more robust transition. Anybody who worked with, say, the original versions of any of these programs will find that, there are definitely kinks that have been worked out on all sides. A lot of that is thanks to our partnership with Autodesk. We're actually an Autodesk Premier partner, and so we've been able to get a hold of their source code and some other information directly from them in order to make these things work the best. All right, so now we've transferred back in. We've got our information back into the model. The member sizes have been updated. And if I come in here and go back to the 4th floor, what we're going to see is that here it's listing I have W8 by 10s at 7'6" on center. But when I come back to my RISA floor model, those aren't W8 by 10s, those are W12 by 22s. Well, if I actually click on the beam in Revit here, we'll see it's a W12 by 22. This is a Revit problem relating to structural beam system tags. I laid these out as what's called a beam system within Revit, and so it thinks that they're all still the same size, but they're actually not. I usually get around this by selecting everything in the model here and using my filter. And so I click on that coffee filter looking icon, and I uncheck everything except for structural beam systems. And then I hit OK, so that chooses those, and I just delete those to get rid of them. Now we want to tag everything so that we get the correct sizes and the such on here. So I'm going to come up to Annotate up at the top. We're going to go to Beam Annotations. Before I do that, I actually need to load in some tags that we give you with the link. So I'm going to come to Insert, Load Family, and I'm going to navigate myself to the RISA folder. We're going to go to the RISA-Revit Link 2012 folder, the Beam Tags subfolder, and we're going to select all of these tags and hit Open, and that's going to load them into this model. So once those tags are loaded in, then I can actually use them. And if you want, you can load those into your Revit defaults. We explain how in the help file and the user's manual. So next, I can come back to Annotate. We're going to do beam annotations. I'm going to tell the program I want to remove existing beam tags. And on the upper left part of all beams, I want to use the start reactions. And on the upper right corner, I want to use the end reactions. And these are actually both what we would call end reactions, but start and end refer to the I and J end of the beam. And then I want the beam size above. And down below, I want to use studs and camber. Once again, I know I'm going fast through this, but this is all outlined in the help file. And so now when I hit OK, it's going to come through and tag everything with the information we had from RISA. So we come over here, W12 by 22, 12 studs, 2 1/4 camber. Same thing in Revit. So all that information has now been processed back and forth correctly. So this is how we tag everything, and at this point I can actually take that fourth floor if I want to in Revit, and I can throw it on a sheet so that we can actually put our drawing together right now given all the information that we just brought in from RISA. So there we go. Now it's on the sheet. Now everything is live linked with this. And if I were to go back to RISA at this point and then come back into Revit, basically performing a second round trip, it would update all the information on these sheets automatically, so we wouldn't have to worry about any issues with that. Okay, the last thing that we want to talk about here is that canopy that we had sitting out front. So if I come back out here, I had set this canopy to have no analytical model whatsoever. And currently I have it set as a group. I'm going to sort of explode that group here so that I can select everything that's part of this canopy minus these columns, which I accidentally grabbed over here. And we can choose to enable analytical. So now I've actually turned on the analytical model for this whole canopy. The reason that the link was ignoring it before was because it did not see an analytical model set up. But now when we come to the analytical model view, voila. Here's our whole canopy set up. And I actually want to do a completely separate analysis for that. And the way I'm going to do it is I'm going to select in this 3D view only the canopy. So you can see everything there is highlighted in blue. It's selected. Nothing else in my structure is selected at all. I'm going to come up to add-ins here, and I'm going to say export to RISA once again. Only this time, we're going to export to RISA 3D. We're going to export to a new Exchange file that I'm going to call Canopy. And I have this option to export selected items only. So in this case, I only want to export the canopy, nothing else. That's why I have it selected in blue on screen and nothing else. And so now when I hit OK, let me close out of RISA Floor first so that we can correctly launch RISA 3D. It's going to export this canopy for a totally separate structural analysis, the results of which we can bring back into that same Revit model. So this allows us to break things up, and of course this is going to be much better than having all of our diaphragms and 3D seismic and wind and everything applied to this little canopy, which we're going to design in a separate manner anyhow. So now at this point, I would just solve this model within RISA 3D, and I would import it right back into Revit. But there's a very critical step here. When I come back into Revit, I need to make sure to update member sizes only. The reason behind this is that if we do a full geometry import back into the Revit model, what's going to happen is the Revit model is going to say, all right, I see a canopy and I see nothing else. So we need to make the Revit model match that. And it will make this a canopy and nothing else by deleting everything else that we have in the model here. So it's very important that if you do these little side exports that you always only update member sizes only. Now, the other way to get around that, if we did have a true geometry change in this canopy, would be to temporarily shut off the analytical model for literally the rest of the building. Because when we do transfers back and forth, we completely ignore anything that's set to be non-analytical or not for analysis. All right, so the last point to bring up that I was going to mention is what is important when you start off in RISA. We've taken a look at starting off in Revit, and most of the concepts apply much the same as what we've seen back and forth here. But there is one critical thing that you need to take a look at when you start in RISA, as opposed to the many critical things you need to take a look at when you start in Revit. And that is your member type. I'm going to come up here and color code by member type. And what we see is the green elements are beams, reds are column, and then the pink ones are vertical bracing. Now, when you draw a member in RISA, Most people come in here and they completely ignore this drop-down. They go to draw new members, hot roll. They say, oh, yeah, I want this beam size. I want this design list, this material, whatever. Yeah, fine, beam. And they'll draw their columns all as type beam. They'll draw their braces all as type beam. But it's very important that you differentiate between a beam, a V-brace, which is a brace in a vertical plane, and a column, or an H-brace, a brace in a horizontal plane, because Revit treats them all differently. And if you draw a vertical element in RISA as a beam, and then you import it into Revit, Revit will get very confused and say, well, a beam can't be vertical, I'm just going to delete it. And then it's going to start blowing away that part of your model, which is the last thing you want. So it's a very important consideration to make when you're going back and forth. That covers basically all the topics that we wanted to hit today with this presentation. So at this point, I'd just like to let you know that we do have additional resources available. Aside from the help file that I pointed out, and the RISA-Revit Link User's Manual, which that PDF is available both on our website and in the installed folder, you can also come to our website, risatech.com, and we offer full technical support on the link as well, so you can call us up and ask us any questions you have, or if you're having any difficulties. I'd just like to mention that if you are submitting a Revit model to us that you're having a problem with, I run into this all the time, please relinquish all of your work sets and, if possible, send me the central model, because otherwise, of course, I run into all sorts of permissions issues when I go in and try to figure out what you need to do to fix your model. But if you get in and play around with the link, it's all very self-explanatory, and you should be able to get the hang of it pretty quickly.